So, good afternoon. So it's a pleasure for me to give you this presentation today. So I decided to choose a topic to remember a little bit one of my first work related to microelectronics, that was reverse engineering, and how this reverse engineering inspires some of the works that we have done after that till nowadays. So first, talking about the past. So in part of 79 to 80, I have done the reverse engineering of the Z8000. That was a Zilog 16-bit microprocessor. In reality, the same chip was sold as Z8001 and Z8002. So, but the chip was the same. There was just a metal connection between two pins to select one or another during the packaging of the chip. So one interesting point in this Z8000, at the same time people were looking how many instructions were really used in running some applications in the microprocessor. They found that 4 instructions were responsible for about 40% of the instructions being used. And then they decided to divide the control part in 2 parts. So one part was just to take care of these 4 instructions, and the other was to take care of the other about 100 instructions. So as you can see, this microprocessor, in the top we can see the data path, and about 75% of the area was dedicated to the control part that was done using random logic. In all this control part was designed by hand. So then I have done a set of photos using a Polaroid machine, and this Polaroid machine was attached to an optical microscope. Then I have done a large set of photos, and then I put them all together, generating a mosaic with about 2 by 2 meters. And then also using a lens, I was able to identify when there was a polysilicon crossing a diffusion. And then when a transistor was recognized, it was labeled. Then it was observed the connections between these transistors, letting the identification of the logic gates, and then the connection between logic gates to identify functions and so on. It was a very nice experience where I was able to see a lot of things that were not available anywhere else. No. Here is another detail of the control part, completely in random logic. So it was composed by high density of gates. You don't see many empty spaces, and we were able to find some gates with about 23 inputs. And so the main optimization of the layout was done by using super gates. So as they were not using a cell library in one, they have done the design of any gate that was needed. There was also the use of lines in 45 degrees. The vertical connections were mainly using polysilicon because it was just one metal layer technology, 3.5 microns. And we can find the row of cells with more than 20 tracks. So you see the top one, where you can see VDD and ground, and the number of tracks that are running over this set of cells is quite big. And these metal lines were metal lines containing definition of instructions, but also the timing that was divided in 2 levels of timing in this microprocessor. So here is another detail. And what was interesting, I don't have here the exact photo of some example, but sometimes a super gate was divided in 2 or even 3 parts, and one part was implemented in one location, and the other part in another location of the control block, and these 2 parts were connected by a metal one. So it's not a common design to do a gate that is split in 2 or more locations of the layout. Also, the same logic gate, for example, an AND with let's say 3 inputs. Each time it was designed an AND with 3 inputs. The layout and the size was different depending where it was located. Here is another detail of some other circuits that I have looked at the microscope. Several of them we took out the metal lines, so we have only some silicon oxide under the metal that we can see where the metal was. And even in this one you can see that several lines have had also 45 degrees and so on, and so there was a nice work to try to optimize everything that was possible. Here is the 68000. So also here we can see several diffusions that with shapes that are not find nowadays. So you see different formats. So here the diffusion is the orange one. So there was a huge work to define the shape of any diffusion zone. Here is another view. You can also see in the top some buses using 45 degrees. Here again. Here is a photo of 6809. So there is still some metals in some contacts. And here is interesting because we can see that the sizing of, this is a memory bit. The size of any signal transistor are completely different. And with also a small transistor that is being used to do a resistance between one of the feedbacks. So here is the TMS 7000. So this is also very compact. So it's an example, another example that of a control part that was fully designed by hand. So the challenge is how we can do automatic synthesis with a so dense, producing a so dense layout. For sure, nowadays we have a lot of restriction in the design rules in modern technology. But in one hand, there is still some things that we can do. And another one is that for the future, maybe we can have some other technology that will allow us also to increase the compaction. The observation of all these circuits designed by hand was an inspiration to search for tools that could provide a so dense layout as the one designed by hand. Then we have done a first publication during my PhD. So my advisor was Professor François Anceau, and you can see here a paper published in '82 at Solid State Circuits, Journal of Solid State Circuits. And the first figure that you can see better here was proposing to do the routing over the cells. So to do a full over the cells routing, even using one metal layer that time. That was the technology available. So on the right here you can see the traditional standard cell approach that was starting to be used at that time, where we could find space between the cell rows to do the routing between these rows. And our approach that we start using in our group was to cross all the connections over the cells and then to have all the cells rows placed one over the other. No? So for sure, in this case, a VDD line was shared between two rows of cells, and the same for the ground one. And then we start doing some tools by that time, 83, 84, where we use also track priority management. So, for example, one track had a priority for connections between other cells, so crossing one cell, and for the connections that are short ones inside cells or between neighboring cells. All these short connections use the tracks with priority for these small connections. So then you can see here on the right, so it was able, so this was published in ISCA 88. So an example of synthesis of layout where we have a nice compaction using this routing over the cells. Here is another example. So this was using another work developed in our group, and it was a novelty solution, let's say, that time, in the same time that the industry was still using routing channels between the rows of cells. Here is some other works that were done after. So on the left was Tropic by Fernando Moraes, and Parrot by Cristiano Lazzari. So you can see that from Tropic to Parrot we were able to increase a lot the density. And here is another block. So all these designs were done at just one, taking as the full design of the full block. So the problem is when the block was increasing, functional block was increasing the size, the running time was increasing a lot. So then we decided to move, but now I will present some new reasons to improve optimization of the circuits. So in the beginning, our main target was to reduce the area of the chip. So, but also reducing delay and so. But now we have a major point that allow us to really move to have a new layout strategy. So, for example, you see nowadays, in 2022 is estimated to have the production of about 86 trillion transistors in the world. If you see here, compare 2014 to 2017, that are real data. From 2014, we had 250 quintillions transistors produced in the world. 3 years after, we had 4 times more. So this is keep increasing. So till when we were able to increase this, are we going to have a sufficient power supply to run all these transistors? And how many power plants we will need to cope with this IoT world? So this is a major issue. And then nowadays a major point is to do the optimization of all the implementation. This optimization should be done in all levels of abstraction. And one reason that we can say that optimization is a key word in nano-CMOS is that more and more we need embedded system that requires low power. And the way to have low power is to have dedicated optimized ASICs. So nowadays we can find a lot of nice circuits that are using much more transistor than is needed. So the main goal in this work is to reduce the number of transistors and connections in a chip. Connections also because the amount of connections is also a problem in many of the modern design. So it will be great also to reduce the number of connections. So here is it was published in ICCAD a long time ago, and we can see here the number of functions that we can have by using 4 stacked NMOS transistor and 4 stacked PMOS transistor. It's in red, is more than 3,500 different options. And we see nowadays that the cell libraries normally have less than 100 functions, only 3 sizings. And so reducing the space to do optimization of the logic, and for consequence the optimization of the number of transistors. So here is a small example. So implementing this small equation here, we have 4 gates using 14 transistors, but using just one super gate. So just one gate, you can put exactly the same function, 8 transistors, and 3 connections less also. So the connections between the gates here that we need to go to metal layer to do, then we are not going to need to do anymore. And also we have a reduction in the number of vias. So in all these also help to reduce routing congestion. So this is another interesting point of using more super gates or complex. In modern technologies, we consider that we need less transistors, and that means less static power. So less connections in vias helps improving routing, this is for sure. And then we consider that we should move from the physical design as a place and route of cells from a library to have a place and route of transistors. So the design of a network of transistors. So one of the tools that were developed in our group was Astran, that supports transistor fold and transistor sizing. So here is an example of some cells that were designed completely automatically. So a flip-flop also. Doing the design of each cell separately. It could even be done using different computer or so in parallel. And what was interesting here is also that showing this example that a simple multiplier, that there was a reduction in the number of cells, but the main point is the reduction on the number of transistors, and this reduction of the number of transistors was the main reason to a nice reduction in power consumption. So here you cannot see with my camera, but so another point that we verified is that doing different transistor arrangement, so without changing anything on the logic of the circuit. So for example here, if you have the 8 transistors that is close to the output or far to the output, so this changed nothing to the equation or to the function, but there is a change in the sensibility to radiation effects of each point. So when we are doing circuits that we want to have then with tolerance to radiation effects, then it's interesting also to look at this issue. We're also doing this transistor reordering. So here we have the same function, but with a different transistor ordering. And you can see that the layout, mainly looking here, the metal layers, they are different. So this, for sure, one of them will be the better solution for the considering radiation effects. But also we have here 4 options that can also be used if you wanted to give more difficulty for someone that is still willing to do reverse engineering of the circuit. Then they will find more options for each function. So for sure, not all layout optimization done in the past using NMOS transistors. Nodes can be done when using nowadays technology that are much more restrictive, that have much more restrictive design rules. But there is several issues that we can be inspired by the old microprocessor designed by hand. So nowadays we have no tools that can have the same compaction that was done by hand in the past. And for sure you cannot do a design by hand nowadays due to the size of most of the circuits now. And we also don't know what will be the technology we are going to have in the future. So it will be interesting if you have a new technology where you can have just one transistor from the output to VDD, like an old NMOS, and then we will be able to do much more complex gate with a larger set of inputs. So some conclusions: a way to reduce power consumption is to reduce the amount of transistors. And a way to reduce the amount of transistor is to use super gates. So, and also with this, we give freedom to people working in logic synthesis, where they are able to do all the logic optimization they can, without the restrictions of mapping these functions to the ones available in a cell library. So this is can be a good improvement. Also, we can repeat here that we consider that a keyword nowadays in non-electronics is optimization, something that is not a main target in many of the circuits design in the past and even today. So let's do physical design as a design of a network of transistors. That means placing route of transistors and not placing route of cells from a library. Something else. So first, I'd like to thank all students that have worked or are working in our research group. So I'm very lucky to find here in Brazil and also in South America very clever students that have done a very nice work. And also to my colleague, Professor Marcelo Johan, that is a great partner in EDA, research in education. So he was also co-advisor of several of students that I had the opportunity to be an advisor. And just to show you here some of my former graduate students, so I not including here the undergrad student that I should include in the next version, where they are working now. So Renato Hench, that just gave the talk, he's now with Synopsys, but he worked for more than 10 years with Intel. Henrique is in Synopsys in Canada. Guilherme Flax is Synopsys USA. We have also Lucas that is in NXP, and Thiago in Roku. I'm not going to read all the names, but you can see here that they are spread in several companies in North America, in Europe, and also here in Porto Alegre, that is now the main location for microelectronics in South America. So Rio Intent has a development office here, like in Silica, like Silvaco, like Impinj. So here some others, former student, Gustavo that was first with Intel, then Synopsys, now is with Google. Igor is with CERN in Geneva, and so on. And we have also a nice set of PhD students that now are professors in some universities in Brazil, in Europe, and also in other countries of Latin America. And also I invite you to see more about some photos that I have done in the past. I have rescanned all the slides a few years ago to present some of the pictures in the Dark Art Show, and then in this in this Facebook page you can see much more. And a curiosity is this one here, where I left too much time in the ASTI, so and then the polysilicon was also going away. So thank you very much again. It is a great pleasure for me to give this talk today, and I would like to thank the ISPD committee to be so gentle to give this surprise to me, giving this award that, as I told you, I have to share with all my students and colleagues. So thank you very much. Bye-bye.